Hey everyone, welcome back to my channel. So remember this video? In that video, I asked myself why there is no classification model that uses only LSTM. If it uses LSTM, it's usually combined with other types of neural network. To the best of my knowledge, it's usually combined with convolutional neural network. There are several models that combines them. And today in this video, we're going to learn one of them, that is multivariate LSTM-FCNs for time series classification. Moreover, I'm going to share my opinion a little bit about why there's no such model that uses only LSTM. And then finally, we're going to apply this model to predict the probability that a company goes bankrupt. The data is highly imbalanced, so it's going to be a bit difficult. I personally believe, I'm not sure if this is a successful project. Okay, now let's study together. Okay, so the name of the model is Multivariate LSTM-FCNs for time series classification. It's shortened as MLSTM-FCN. I sometimes think about it as a jumble of letters, but no. Okay, so M and then LSTM and FCN. So multivariate, because this model accepts multivariate time series as its input. It's actually an extension of the univariate version. So the univariate version is called LSTM-FCNs only, but this time it's called multivariate. So it deals with multivariate inputs. And then, as the name suggests, it has LSTM part, the LSTM part, and the convolutional network part. The LSTM part here can be replaced with an attention layer. So if we use attention, it will be called ALSTM-FCN. Attention LSTM-FCN. Okay, so let's see the whole network. This is the whole network. You can see that on the left side we have the convolutional block, and on the right side this is the LSTM block. The input will go into both blocks at the same time, and the results are concatenated here, and then go through a dense layer to get a predicted label. Now let's refresh our memory of LSTM and convolutional network. As we go along, we look at the details like the order of the layers. This is the landscape layout of the network, and this is what we will see in the original paper. Of course, with the connecting lines. Anyway, okay, so LSTM and FCN, these are the big parts of the model. Let's look at the LSTM first on the left side. This picture is a hidden cell in an LSTM layer. So LSTM layer is a layer or a chain of hidden cells. Usually the total hidden cells is the length of the input, so that each time point has its own hidden cell to process the information that's in the time point. LSTM is designed for sequence input, so it is used to learn the temporal dependencies, and the chains work in a recurrence principle. So the output of a hidden cell, let's say t-1, would be the input of the next hidden cell, let's say the hidden cell of time t. Each hidden cell has several gates. I guess the most important, like the highlight of the LSTM, are the update gate and the forget gate. So in the update gate, each hidden cell asks whether we want to update, we want to use the information that we just get in that time point, at time t, to update our whole information. If so, how many of it that we want to use. And then for the forget gate, it controls how many of the information that we have obtained previously, so from time 0 up to time t-1, that we want to forget. In addition to update and forget gate, we also have the output gate here, and each hidden cell will also output the CT here, the cell output. The cell output is the aggregation between the update gate and the forget gate. I talked about LSTM in more detail previously, and so you can check that out. Now let's move on to convolutional network. For the convolutional network, it works really well in image classification, because convolution layers can capture the shape in image. So in time series or in sequence inputs, convolutional layers are used to capture the shape of the time series. In other words, the fluctuation of it. What we have here is, well, the white array here is the time series, while the orange or the yellow array is the kernel. So a convolution operation is actually just sliding the yellow kernel from left to right, and depending on which element of the kernel is the anchor, we have different types of padding. This particular image shows the same, the valid padding, meaning that we don't want to give any zero padding in the time series. But what we're going to do in this model later is call the same padding. So the anchor of the convolutional operation would be the center of the kernel. In this particular image, it's here, the fourth element. And so the convolution operation would start when the anchor meets the first element of the time series, and end when the anchor or the center of the kernel meets the last element of the time series. So let me show you more concretely. The beginning of the convolution operation would be like 7, 4, minus 1, minus 10, and then this would be the center of the kernel. And then we have 3 values left, right? We have some spaces here, so we pad them with 0. And the same goes for the ending. So the convolution would end when it goes like this. Minus 12, 26, 3, minus 9, and then 0, 0, 0. When the yellow kernel meets this subsequence, that's the end of the convolution. In this channel, I have made a couple of videos talking about convolution. You can check out the rocket and the mini rocket video. The C in mini rocket and rocket is for convolution. Convolutional blocks, like I said earlier, is used to capture the shape. And I guess this is why we don't have a model that uses only LSTM, because LSTM cannot capture the shape of an input. Yeah, but if you've seen that video, you will see that the one that uses LSTM only has the highest performance, has the highest ROC, if I remember it correctly. I don't know why, actually. Maybe that's just a coincidence. Anyway, back to the video. In this block, we also have a squeeze and excite block. Let's look at it. So first of all, the input would go through a convolutional block, and the output of the convolutional block would be the length input times the total kernel. Oh, well, I just wrote F. F is filter. So in this video, I'm going to use the term filter, kernel, and channel interchangeably. They mean the same. Okay, after convolution, we go into the squeeze operation. The squeeze is, well, squeezing. So we take the average of each channel. So we have feature columns, or we have the total filter columns, and each column has a length of input length. So we just take the average out of the length of the input values, so that the output would be one row, and the total columns would be the total filters. Okay, that's squeezing. And then for the excite operation is made to capture the channel-wise dependencies. So in other words, the dependencies among features. The output of excite operation would also be 1 times the total filters, and then we go through a rescale operation. Rescale here is multiplying the output of excite and the convolutional output. So the output would have dimension of length of the input times the total filters. Actually, I have to say that the length of the input here is not going to be the length of the input time series, because we would have permutation in dimension. I'm going to explain that in a moment. But for now, just know that that little operation is only for reducing the computation cost without really compromising the accuracy. Okay, so that's the concept of squeeze and excite. Now let's see this block in terms of the mathematical equation and in the layers. So the upper equation here is the squeeze operation. As we can see here, 1 over t, t is the length of the input, 1 over t times the aggregate or the sum of the values. So it's the average. And when building the network, we use the global average pool layer. Here the C means that we do pooling for every channel or every feature. No, not every feature, sorry, I mean every filter. Yeah, I mean, what I mean by feature is that the input of this would be the total filter, right? So, yeah. Anyway, okay, let's move on. Now the excite operation has 2 layers, because this is the equation of the excite. So first of all, the output of global average pool layer would be trained in a dense layer with ReLU activation function, and then the output of that would be trained using a dense layer with sigmoid function. Okay, so this is how it looks like in the layers. The total hidden unit in the first dense layer would be the total channel or the total filters divided by reduction ratio. The reduction ratio is always 16. Okay, so in other words, the total filters divided by 16. And then for the second dense layer, the total hidden units is the total filters or the total channel. Okay. And then the output of the dense layer using sigmoid function would be rescaled. So it uses the multiply layer. So here's the model again. The squeeze and excite blocks are placed here. So this model has 3 convolutional blocks. At the end of the first 2, we have squeeze and excite blocks. And for the last one, the last convolutional block, we end it with a global average pool. The convolution is convolutional 1D because we're dealing with a time series, and then it's going to be followed by a batch normalization and ReLU activation layer before going to squeeze and excite block or global average pool if we're in the third block. And then we also have discussed this too, the LSTM. After LSTM, it's going to be followed by dropout before going to the concatenation. Okay, this is the permutation that I was talking about earlier. In reality, later, in practice, the permutation is not going to be here. Well, yeah, the permutation is not going to be here. It's going to be around here, actually. But I'm still using this because this is what we will see in the paper. Okay, so the permutation layer is added there to reduce the computation cost. So earlier, the input here, the input would be in 3 dimensions. The first one is the total observations that we have, and then the second is the length of the input. the length of each time series, and then the third one is going to be the total time series at each time point. But after passing through the permutation layer, the dimension here and here, so the second and the third dimension would be swapped. So it's going to be the total observations, and then the second would represent the total variables, and the third would represent the length of the input. You see, permutation or transposing the matrix can reduce the computation cost if the length input is longer than the total time series. In our case, you will see later that the length input is 20, because the length input is 20 years, so it's a yearly data, and we have 20 years, and then we have 18 time series. So when the data set first come into the model, the shape would be 20 for the second dimension and then 18 for the third dimension. But then after swapping it, after transposing it, we would have the shape 18 and then 20 for the second and the third. And so when it goes into the CNN, the convolutional block, it would only need to process 18 values per time series instead of 20. So that's why the computation cost would reduce. And then the result of the permutation would go to LSTM and convolutional blocks. And then lastly, for the dense layer here, it's going to be a dense layer with activation softmax. Okay, so that's the summary of this model. If you want to know more about it, you can check out this paper. Okay, now let's go see the data and try to apply this model into that dataset. Okay, so here we are in Calcul Notebook. Okay, first of all, let's look at the dataset. It's called American Companies Bankruptcy. Okay, so this is the dataset. You can read the description here. It is said that there are two kinds of, or two circumstances of bankrupt, either Chapter 11 or 7. Okay, so this is the variable names like depreciation and amortization, cost of goods sold. You can check out here. So X18, we have 18 time series. A company is labeled as failed if the next year, that company files for bankruptcy. Okay, this is a long format dataset. That's why we have several alive words here for the same company. So as you can see, company 1 is alive. That means it's not going to go bankrupt in the next year. A company would have a complete data if it has the data from 1999 to 2018 over the span of 20 years. While the raw dataset has variable length, we're going to use only the companies which has 20 years of data. Okay, so now let's load the data. First of all, we load the libraries. I load the basic ones first. So from the graph here, we can see that the total companies with a complete data of 20 years is a bit less than 1,200 companies. It's only around 31%. Actually, we can confirm it. Actually, yeah, so if we confirm here, 13%, not 31. So we just take the 13% of the raw data, okay, and we collect the company names in this array, wanted companies. And so this is our final data frame that we will use for the rest of the project. Okay, now let's look at the class distribution. As we can see here, yeah, it's highly imbalanced. 98% of the whole company, of the whole data, is alive after 20 years. Only 1% of them file for bankruptcy the next year. So here, out of all companies in the data frame, only 13 companies failed. Okay, let's move on. Let's split the data. So I'm going to set the test size to be 0.2. And the certify here is needed because we have an imbalanced data. Okay, and then we split the data. And we make them as a non-prime matrix. And also encode the labels because the while earlier was still in strings. In the training data set, we have only 10 companies that goes into bankruptcy. So that means in the validation, we have only 3 companies. But percentage-wise, this is balanced because 3 out of 235. Okay, for this cell, class weights, according to the original paper, if we have imbalanced data, we can use these weights. That's what this cell is about. Okay, now let's do the modeling. For this cell, I'm not sure if this is correct now, but this is what I thought. If we just label all the companies to be alive, because the majority of them are alive anyway, what is the ROC score? Sorry, I mean zeros here. It should be zeros. But the result is the same. I guess this is not surprising given the nature of ROC and AUC score. But I don't know, I'm not sure. I guess this is not right because, I mean, like, now that I think of it, I think we're not supposed to use this as our base. Anyway, okay, so this is the model. Okay, this is the model, and I copied it and modified a little bit from the GitHub from this link. It's from one of the authors of the paper. What I changed the most is the shape and then the total kernels or total filters. They give 128, 256 and 128, but here I just give 32, 64 and 16. And then 8, 5, 3 is the kernel size. Another difference between this code, this implementation and the paper is the masking, but I think it's not going to affect the model. The LSTM is implemented here. LSTM layer with the output size to be 8. I said earlier that the permutation, the output of the permutation layer would go into the LSTM and convolutional, but looking at this code, it's actually just code to the CNN or the convolutional blocks. But they say that it's an equal operation. So, okay. Here is the squeeze and excite block. It's going to be defined here. Yeah. So you can see this is the global average pooling and then followed by a reshape. The reshape here is needed just to make the shape in sync with the next layers. Okay, and then the dense layer, this dense layer has the total filters divided by 16 hidden units, and then the activation is ReLU. For the second one, it has the total filters hidden units, and the activation function is sigmoid. And then lastly, for the rescale, it uses multiply function, multiply layer, sorry. Yeah, it's a multiply layer. Okay, let's run this and let's generate a model. Okay, so for this particular model, we have around 20,000 parameters. Now let's see the representation of this model using diagram. Okay, now let's compile the data and fit it. So the optimizer used is Adam, and then the loss is binary cross entropy, and for the metrics, I used 3 metrics: AUC, accuracy, and F1 score. Even though we all know that accuracy is not a good metric if we have an imbalanced data, but I just want to use accuracy as a benchmark. Because if we give the label all 0, we would have a very high accuracy, which is 98.8%. So let's see whether the prediction can top that. And then for the fit, well, here I set the YT to get the dummies, because YT is actually just an array of either 1 or 0. So this is YT. It's just one column, but here we use softmax, right? So the output has 2 elements, so that's why I have to use this function. Time epochs is just enough. I have tried using more, and the result or the performance is just getting worse. Okay, so this is the accuracy. Notice that we don't use the class weight now. Okay, we're going to compare the results by using and without the class weights. Okay, but for now, let's not use the class weight first and compute the ROC score. Wow, the ROC score is really high. When I tried several times before, it never get to this high. It's usually around 0.7378. 0.64 was the lowest. Of course, getting the exact result in neural network is really hard, so yeah. As you can see, I'm running this in real time, so yeah, this is the real-time result. If you look at the ROC score, it's really high, but I don't know, I tried using other metrics, like for example Matthew's correlation coefficient, or MCC. It's usually used for binary classification, and for that I use the hard labeling, hard prediction, and we get 0.21. Not too bad. In MCC we have 3 values, either -1, 0, or 1. So that's the range. The minimum would be -1 and the maximum would be +1. The best score would be +1, because that indicates a perfect prediction. 0 means that it's just a random average prediction. And since this is 0.21, it's not so great. Now let's see the prediction. What is the hard predicted? And we can see quite a lot of 1s here. Now let's compute the F1 score. It's 0.1. F1 score ranges from 0 to 1. The higher the score, the better the performance is, and so based on F1 score, it's not really great too, 0.1. Okay, now let's see the prediction, the real probability. It's like this. I feel like seeing the real values like this helped me to identify which observation gets labeled 0 and how extreme the probability is. So for example, like this, it's 0.62, so it's quite the model is quite certain that this company is going to fail, rather than like this 0.5. 0.5 means that it's in the middle. It's either yes or no. Well, you know what? We haven't seen the accuracy score, right? Let's take a look at that. The accuracy score is only 0.78. If we give all zeros, then we would have an accuracy score of 0.987. That's why I initially hesitated to do this video, but it's part of my learning process, I guess. Okay, I'm going to show you how the model goes if we use class weights. Probably you have said, yeah, you haven't used the class weights. Class weights is actually really important if we have imbalanced data. Okay, so let's see how it goes. So we generate the model again, and then compile and fit with a class weight as class weights. As we can see, the accuracy value is not as high as the previous fitting, and so does the AUC. Okay, now let's see the ROC AUC. So in the previous fitting, in the previous model without class weights, we have 0.92. Now let's see the ROC score from the weighted model. It's only 0.12. And this is consistent. So what I'm saying is that the ROC score for weighted models is consistently lower than the ones without class weights. I tried running it several times. It is true that in the original paper, none of the data sets deals with a financial data set. I feel like financial data sets are naturally harder to deal with, and maybe LSTM-FCN is not the right model. Anyway, let's see the MCC score. The MCC is minus 0.12. Okay, we can see from the widespread here that the weighted model predicts way more ones than the previous model. That's interesting. Now let's look at the F1 score. It's near 0, so yeah, it's worse. Okay, for this cell, well, we already see the labels here. There are so many ones here, so I'm pretty sure the accuracy score is going to be way lower than 0.78. But okay, let's just see it. 0.21. There you have it. Actually, I haven't made the confusion matrix. So, I don't know, maybe even though we have many ones, but we perhaps have captured the right company to be labeled one. So instead of calculating the precision or recall score, let's just look at which company gets one and whether we have predicted correctly. Okay, so in the valid data set, the failed companies are indexed 25, 63, and 159. Let's see the Y prediction of 25, 63, and 159. 001. Okay, so we, out of these companies, these 3 companies, we only get 1 correct. I didn't get to try it with the model without class weights, but we still have the screen recording of it, so let's take a look at it. The results are in 5 columns and the index starts from 0. So this is the 25th value and this is the 63rd value. The dark green line here is the checkpoint. And the value at the bottom right corner is at index 159. So yeah, we can see that all the labels, if we want to give it a hard labeling, we would have all one. Okay, so far we have trained two models, the unweighted and weighted models. And we have seen that the unweighted version or the unweighted model has better performance. Now it seems like we have the winner model, which is the unweighted model, but the huge caveat is that, as I told you earlier, when I tried experimenting with it before recording, I usually got 0.73 or 0.78. The lowest was 0.64. So the ROC score using unweighted model varies greatly. And this is what we will see in the next clip. Okay, actually we can try it again. But I'm pretty sure we're not going to get 92 again. 0.92 in the ROC. Oh, we have only 0.34 now. This one is 0.63, better. I guess the important takeaway of this project is that it's so hard, and maybe we need to look at this problem from a different perspective, like, for example, anomaly detection. Of course, we can try using different number of filters or different output, different size of LSTM output. That's also another direction to go for. But yeah, now we have seen and studied this model, multivariate LSTM-FCNs, and hopefully you enjoyed this content. If you do, please consider subscribing to my channel, Timely Time Series. I'll see you next time. Bye bye.